We've got more resistors in series and parallel. Okay, so we're looking at another equivalent resistance example. This is the second one we've done. If you haven't seen the first one, go check out that video because we're getting a little bit more complicated. So let's just first draw a circuit, and then we're going to be trying to find the total equivalent resistance of the whole circuit. So what we have here is a 25 volt battery or an EMF. We come up, we hit a little junction point here. There's a poorly drawn resistor, another one, and then here's another one, and then and then we'll just wing this all the way back around. And now let's put in all the values for them. What we've got here is a 25 ohm and a 3 ohm resistor. This resistor is 40, this resistor is 15, and this resistor is 18. So how do we go about solving this setup? Well, if you recall, it's best to dive deep into the parallel branches and then work your way backwards out of them. So let's take a look at this parallel branch that we've got here. The equivalent resistance of a parallel branch, 1 over the equivalent resistance is 1 over, and then one of these resistors, so we'll do 1 over 3, plus 1 over the other resistor, 1 over 25. And when I add those up, I need to make sure that I take the reciprocal of this, okay? I need to make sure I flip this in the end. So after I flip this properly, so I take like 1 over all of that, I'm going to get 2.68 ohms. That is the biggest thing my students miss. They forget to flip this once they have it set up. They have 1 over 3 plus 1 over 25. They forget to take 1 over that quantity, okay? Now, if you're struggling with some of these circuits, what I would recommend is every time you solve for an equivalent resistor of a piece, redraw the whole thing. So let's just do that, and we'll do it over here in burgundy. So here's the 20. This is the 2.68. Who do we appreciate? Lord Restob. Here is the 40, and then here's the branch here for the 15 and the 18. I'll bring that all the way around. Okay, so if we're looking at that now, this is our redrawn circuit. Well, the 2.68 and the 40 ohms, those are in series with one another, but I still have this parallel branch down there, so let's fix the parallel branch. Let's fix this 15 and the 18. So following the same procedure as before, 1 over the equivalent resistance is 1 over 15 plus 1 over 18. Don't forget to pull the flip move. We'll find that the equivalent resistance for this is going to be 8.18. Okay? Now, if you're like, how do I know 8.18 could even be right? Like, that seems a little small. I had 15 and I had 18. Can it actually be that small? Well, in both our prior example, the one up here in blue, and in this example, the one here in pink, the 8.18, both of these values are smaller than the smallest resistor in the parallel branch. That must always occur. When you have a parallel branch, the equivalent resistance must be less than the smallest resistor. So here, that smallest resistor was 3. Our answer, 2.68 for that, is smaller. That's good. Over here, we've got a 15 and an 18. Our value of 8 is indeed smaller than both of those. So we can feel confident that those values are good. So let's just redraw our entire circuit again. We'll do it in blue. There's the battery. There's the 2.68. Here's the 40. And it doesn't matter if I draw this here going down or if I draw it going over. So I'll just draw it going over. The wires mean nothing. It's just a matter of like setting things up in terms of how it visually looks to you. And now I've got all 3 of the resistors. So up here, the 2.68 was one equivalent, the 8.18 was an equivalent, and now these are all in series, so I can just add them together. I can just say that the equivalent resistance of everything in series is 40 plus 2.68 plus 8.18, and that will give me an equivalent resistance of just over 50. It's about 50.9 ohms. Okay? So now, if we wanted to truly like rewrite this as one final circuit here, there's our battery, here's our resistor, and that's it, where this is 50.9 ohms, and I believe our battery was 25, but we'll just go and check. Yeah, it was a 25 volt battery. Boom. Oops, 25 volt battery. And remember, that follows Ohm's law, V equals IR, which 25 would equal some current flowing through this times the 50.9 ohms. And if we wanted to, we could solve for I. Then, the current here would just be approximately 0.5 amps in this case. Okay, so that's how we go about doing this. We go into our parallel branches first. We be very careful about finding their equivalent resistance, because we need to note that we need to take the reciprocal of that final addition that we have. So make sure you're doing that. If you're struggling with these, make sure you're redrawing the circuits like we did here in burgundy, and then we did once again in blue. And then once we get them all in series, it's just a simple matter of adding them up and finding that final answer. Okay, so that was the second one we've done. We'll take a look at a few more complicated things coming up in some next videos. In the next videos, what we'll also be looking at is, if I've got 25 volts going around this battery, where is it actually losing the voltage? How much voltage is it losing across this piece? How much voltage is it losing across the next? Can we figure those voltage drops individually across resistors and components out as we're going around our circuits? So that's what we're looking at next. It gets a little bit more complicated with what we're doing here, but in the end, it is just Ohm's law. But that's our next video. For now, this is finished. Adios. Take it easy.